Okay, so XFLR5, it, yeah, so this is the wiki on NACA airfoil, so if you want to go to this wiki and read it, there's a lot of really good stuff on there. I would encourage you to read it. XFLR5 is a free program, and it allows you to analyze the entire aircraft as a whole. XFLR5 has XFoil inside of it, and XFoil is a 2D aerodynamic analysis tool. I have, thanks to one of my students, I have a tutorial on, well, I don't have it. I didn't write it. I have a tutorial on two programs called DATCOM and XFLR5. DATCOM is written in Fortran, and you have to compile it. I don't recommend it. It does the same thing. But XFLR5, let me scroll down to XFLR5. Here's XFLR5. You can do 2D airfoil design here. You can make lift and drag plots, and you can actually put in your entire aircraft into it, and it will compute you things like lift and drag. And I think what this does is it uses what's called a vortex lattice method, and so it assumes that every quadrature is a lifting surface, and it computes lift and drag on that and adds it all together for you. It's a really cool program. If you go through this tutorial, hopefully you'll learn how to use it. I'm just going to show you just a quick 2D airfoil analysis. So I'm in Linux, so I'm going to type in XFLR5. In Windows, it'll probably be a little bit different. But it's going to bring up this black window. So if I head up to File, or I'm going to do XFoil Direct Analysis. Oh, that's not what I wanted. Direct foil design. So I'm going to design my airfoil first. And so I'm going to right-click. Again, this is all in my tutorial. I just kind of want to show you. I'm going to do foil, NACA foil, and so you can do 4 or 5 digits. So I'm going to do a 0012 first. And for some reason, I think I have a bug in my code. When I type in 0012, it changes it to a 0010. But whatever. If you notice, it's a symmetric airfoil. Maximum thickness is 10. If we add another foil, let's do something crazy like a 4212. So what's the first number again? So that's 4% camber at 20% from the leading edge with 12% thickness. So there you go. Look at that. So there's like a lot of camber, and it's thicker. Well, no, it's still a 4212, but this is a 0010. So this is 10% thickness. This is 12% thickness. But what do you notice about this wing? That looks kind of similar to that one, right? It's kind of flat on the bottom and then curved at the top, right? All right. So then from here, you can go to File, and then I think this is XFoil Direct Analysis. And then you can go to Analysis. Is it Batch Analysis? Yeah, Batch Analysis, Foil List. I'm going to select both of my airfoils. There is this thing called Reynolds number. So many things, right? Reynolds number is equal to the density of the air, the velocity of the aircraft, some unit length. People like to use the chord length sometimes, so I'm just going to replace that with V and C, divided by the viscosity of the air. All right, so viscosity of the air is relatively constant. Density of the air is relatively constant. So the only thing you can change is V and C. If you're the same aircraft and your chord is constant, the only thing you can really change is V. Well, the way it turns out is that aerodynamic phenomena is strongly correlated with how fast you're flying. And so what people do is they write Reynolds numbers of like 100,000, 200,000. It even goes up to like 2 million and 3 million. Those are like really fast Reynolds number. Bees operate in a very, like buzzing bees, the ones that sting you. They operate at a very, very low Reynolds number. Why? Because they're not flying very fast. So there's a lot of research going on now into low Reynolds number aerodynamics. These are sort of like mid-range aerodynamics, so things are pretty well known. And then you've got hyperspeed aerodynamics or hypersonic aerodynamics where the Reynolds number is huge. It's in the millions and tens of millions. I'm going to run a just really simple one from 100,000 to 200,000 in an increment of 10,000. I'm going to set my Mach number to 0.1. I'm assuming I'm not flying very fast. You guys know what Mach number is? Speed of sound. Speed of sound it's the velocity of your aircraft divided by the speed of sound. So if you're flying at the speed of sound, your Mach number is 1. If it's 0.1, it means you're flying at 10% the speed of sound. The speed of sound at sea level is like 320-ish meters per second, so a Mach number of 0.1 would be like 30 meters per second, which would be like, what, 40, 50 miles an hour? So probably a little bit bigger than this one, but that's okay. And then we're going to I'm going to specify the angle of attack range, so I'm going to have it vary the angle of attack from -6 to 12. What happens if I go really, really big on the angle of attack?
You're going to stall.
You're going to stall, right? So if I, let's see, I think I have a video on this, stalling, yeah. So what these things are, they're just like threads or yarn, and they put them on the wing. And so when a piece of yarn is so light, it's going to go in the direction of the flow, right? So whatever the flow is doing, the yarn is going to do. So what this guy is going to do is he's actually going to pitch up his aircraft, change his angle of attack, and he's going to change his angle of attack so large that the yarn is going to start to freak out. Yeah, so you see what's happening here? So what's happening is the flow is actually recirculating. It's not attached anymore. It's recirculating. It's making that yarn freak out. So you might think like, oh, if I get an angle of attack of say 20, then I'll be fine. You can't fly at an angle of attack of 20. The flow won't attach, right? You want the if I'm an air molecule here minding my own business, I want to just kind of travel over like this, no problem, right? You give me an airfoil that looks like this, I'm going to say F you and do this, right? So you can't fly at an angle of attack that's that large. Make sense? So when you get something, if you get a cruise angle of attack of like 8, I'd be a little concerned. You know, you want like 3, 4, 5 maybe for a cruise angle of attack. Like the angle of attack you need is not that large. All right, so let's go back to XFLR5. So I've got my angle of attack window, -6 to 12. I got my Reynolds number window. I got my foil list. So I'm going to hit Analyze. And the cool thing about this is that I think this was actually written in Fortran back in the day, but they compiled it. So it's actually going to use a numerical solver. Yeah, so it actually matters, learning all this stuff, but it does it for you. So I'm going to hit Analyze, and it's going to converge all of these things. And you can even see how many iterations it takes to converge. And if you notice, it's plotting CL versus alpha. This is lift as a function of chord length. So imagine that the wing is sitting right here. So the wing is here and the flow is moving this way. So this is how much lift I'm getting here. I've got my lift to drag slopes here. I've got my pitch moment slopes here. And I think this is doing it for 2 airfoils. So if you notice, this was the symmetric airfoil. So at an angle of attack of 0, I've got no lift. But for my cambered airfoil, at an angle of attack of 0, I do have lift, right? Because it's cambered. And you'll notice that the lift distribution is completely different for the 2 wings, right? What else is different? My lift to drag ratio is completely different. And if you notice, where is my maximum lift to drag ratio? Around an angle of attack of 4. So that's why I was telling you that ballpark. If you start getting into like an angle of attack of 8, you're killing your lift to drag ratio. You want to be around 3 or 4 so that you maximize your lift to drag ratio. Because lift to drag ratio is how much lift you have versus drag. Drag is bad. Drag takes away energy from your system. The more energy taken away from your system, the more thrust you have to add to the system to keep going, which means you aren't going to fly as far. Your battery is only going to last like 8 or 9 minutes. And you have 8 or 9 minutes to get around that course, 10 times or 3 times. What do you guys think?
Interesting.
So you can get in here and you can play with this, change the airfoils, figure out which one you want. I think one of the guys on, or it was a girl, Marcia, she was the expert on the airfoil analysis, and she went through this program and determined which one she wanted it, fed it to all the different teams, and then they sort of designed their aircraft there. Questions? Cool? This is also free, which is awesome, right? I think you can, I don't want to say that. I think it was MIT. I might be wrong. Someone put this together.
Can you explain the bottom left one?
Oh, the CM, the
Yeah.
pitching moment curve. So do you remember in structures, like if I have a beam like this, and say it's attached to the wall, and this is a distributed load like this?
Yeah.
What do you always do to a distributed load? You remember?
Yeah, you find the center.
Find the center and the total force, right? So you integrate across the entire thing, find the area under the curve, and you'll get the total lift. And you'll also find out where that acts, right? If I have lift at a certain point, what's that going to do here?
It's going to cause a moment.
It's going to cause a moment, right? That's what this is here. This is the pitch moment as a function of angle of attack, and it's all over the place.
Okay.
If you are very, very close, it's linear. Everything is linear close to the axis. You know, here's where you stall. Here's where you stall. This is fairly linear. This is a pressure distribution, so that's not. This is nonlinear because where's the drag polar? Am I covering it? There we go. This is this is CL on the y-axis and CD on this axis. So you can see. So here's for the 0012. It's a pretty nice bucket, right? But it basically means if I increase lift more and more and more, you're sooner or later going to stall, and you're not going to get very much lift, but you're also going to diverge, and you're going to get a ton of drag, which is why your lift to drag ratio, which is down here, which is why it peaks and then drops down. If you look at that's like what, 5 degrees? So if we move this out of the way, let's see, so at 5 degrees, I've got about, what, 0.6. At 5 degree angle of attack, my lift coefficient is 0.6. So if I come over here and I look at 0.6, here's my drag, and what do you notice? That's kind of an inflection point. That's right where my drag starts to shoot off, which is why here at 5, that's where my peak lift to drag ratio is, and then my lift to drag ratio starts to drop. Cool? This is neat, honestly. It's a lot. I said crash course. That's why it's on video. You just go back and watch it again. Play it on, like, you know, when you're laying in bed, play it. Headphones.
Leave it on the loop.
Leave it on a loop. Yeah, exactly. Let's see. I think we're done with that. Go ahead and move on to the next section.